Drop a like and do share. Leave your comments and do not forget to subscribe for more videos.
Hi everyone, welcome back to the course on Introduction to Material Science and Engineering offered by Edupedia World. We have been discussing about phase diagram and phases in the present chapter. Last lecture we discussed about invariant reaction, which is known as eutectic reaction, and we saw a phase diagram where eutectic reaction takes place. Today we will discuss another couple of invariant reactions, namely Eutectoid reaction and Peritectic reaction. So let's begin our discussion. First of all, I would like to introduce you to the couple of reactions. Eutectoid reaction is something like this, where a solid reacts and gives rise to two solids. Whereas a peritectic reaction is one where a liquid and a solid react to give a single liquid, rather a single solid. Okay, just to remind you, eutectic reaction was liquid giving rise to two different solid. So when we compare eutectic reaction and eutectoid reaction, what we see is that in eutectic reaction, one of the reactant was in the liquid phase, and liquid phase give rise to two different solid phases. Whereas in eutectoid, the reactant is also in the solid phase, and similar to eutectic reaction, it is giving rise to two solids. So basically the only difference is in eutectic the reactant was liquid, in eutectoid the reactant is solid. Whereas in peritectic reaction, what we have is a liquid and a solid combines to give a different solid phase altogether. I'd like to drive home a point that any reaction, any invariant reaction which has a liquid phase involved in it ends with the tic, like eutectic and peritectic. So this shows that one of the components, one of the phases involved is in the liquid phase. Whereas if we have toid, the ending as toid, then all the reactants are in the solid phase. There is no liquid phase involved. Similarly, we have monotectic, monotectoid. We will not go into the details of those. Okay, now let's see them appearing in the phase diagram. Let's see eutectoid and peritectic appearing in the phase diagram. So here, as I said, eutectoid is one solid to two solids. This phase over here is the delta phase. Okay, this phase is delta phase. This is a single phase region, and this is the invariant reaction at 558 degrees Celsius. This transformation is the invariant transformation, which is giving rise to gamma and epsilon phase. So this reaction, delta solid giving rise to gamma and epsilon solid phases, is the eutectoid reaction. We'll see that eutectoid reaction also takes place in the iron carbon phase diagram when we study it. I had already mentioned that eutectic reaction takes place in the iron carbon phase diagram. Eutectoid reaction also takes place in the iron carbon phase diagram. Similar to the formation of two solids in the eutectic reaction, the two solids formed in the eutectoid reaction is also lamellar in structure, because even here one solid needs to simultaneously give rise to two new solids. Therefore, the grains cannot be independent of each other. They need to be forming simultaneously. Thereby what happens, in the eutectic we had liquid to start with, but in eutectoid we have solid. So what will happen here is, suppose to begin with we had delta phase, right? This was delta phase. Once we cool it to eutectoid temperature, what will happen is nucleation will take place at the grain boundary, because grain boundary nucleation is much easier because the energy required for nucleation at grain boundary is lesser than nucleation required for bulk nucleation. So nucleation will take place at the grain boundary, and then the new grains, the gamma and the epsilon grains, will start to grow at the expense of the old delta grains, and they will grow in lamellar structure. At the end of the reaction, what will happen is the whole delta, this delta will be replaced by lamellar gamma and epsilon like this. The whole, there will be no delta anymore, it will be gamma and epsilon. The whole structure will be like that. Okay. And similar to the case of eutectic reaction, where even if we did not go exactly at that composition, even if we were at a different composition, the ultimate, the last bit of solid that will remain in the form of delta will be of the eutectoid composition, and the rest delta that now is at eutectoid composition will give rise to gamma and epsilon, similar to the case of eutectic reaction. Okay, we'll revisit this when we discuss about iron carbon phase diagram. The peritectic reaction, on the other hand, is one liquid plus one solid giving rise to a single solid phase. This is delta plus liquid, this is single phase epsilon. This reaction over here which is taking place is the peritectic reaction. This is our peritectic reaction, whereby delta plus liquid gives rise to epsilon. Okay, the peritectic reaction also occurs in the iron carbon phase diagram. So all the three invariant reactions which we have studied till now, eutectic, eutectoid and peritectic reaction, all the three will be occurring in the iron carbon phase diagram. With these two new invariant reactions introduced to you, let us now jump into some other details about phase diagram and phase transformations. To begin with, let's understand what is congruent phase transformation and what is incongruent phase transformation. Congruent phase transformation refers to those phase transformation which does not involve any change in composition. So no change in composition involved. Examples of such transformation: allotropic transformation. Allotropic transformation basically means there are certain elements or certain metals which exist in different allotropic forms. Like iron can exist as in the alpha form, it is body centered cubic, whereas in gamma form it is face centered cubic. So this transformation of alpha iron to gamma iron, or the other way around, is a congruent phase transformation, because the composition does not change but the phase is changing. Again, the melting of a pure metal, let's say we have a pure iron and we heat it to 1538 degrees Celsius. This is solid, we get iron in the liquid form. Iron remains iron, this is 100% iron, this is 100% iron, there is no change in composition, but there is a change in phase from the solid to the liquid phase. Therefore this transformation is also a congruent phase transformation. On the other hand, incongruent phase transformation is one where at least one phase has a change in composition. So if any of the involved phases changes its composition, then we have what is known as incongruent phase transformation. Examples: almost all the reactions we discussed till now, eutectic reaction, eutectoid reaction, all of them have a change in composition, so they belong to congruent phase transformation. Then again, melting in an intermediate composition in isomorphous system, like if we have a isomorphous system and melting takes place, as soon as it enters the region, the two phases starts having different composition than the original phase, right? Therefore there is a change in composition. Thereby this reaction is also a invariant phase transformation. I hope this makes abundantly clear what is the difference between congruent and incongruent phase transformation. Now this is one of the important rules. I have briefly mentioned about this Gibbs phase rule. Gibbs phase rule tries to relate the degree of freedom that is available and given C number of components and P number of phases. Now what is degree of freedom? Degree of freedom basically refers to the number of parameters that can be varied independently and simultaneously without affecting one another. Okay, I will explain you the whole idea of Gibbs phase rule using the phase diagram for water. But let me state out the rule. What exactly is the rule? The rule tells that number of degree of freedom is component. C is number of component minus number of phases plus 2. You might ask, where does the plus 2 comes from? The plus 2 is basically one contribution from temperature and another contribution from pressure. So if pressure and temperature can be variables, then we add a plus 2 over here. In case of solid state physics, in case of solid state materials, like the things which we'll mainly discuss in material science and metallurgy, pressure is mostly constant. We work under standard pressure conditions. So instead of F is equal to C minus P plus 2, we take pressure constant, and thereby what we get is a modified Gibbs phase rule, which is F is equal to C minus P plus 1. We remove pressure. This is the case in most of the solid phase diagrams which we'll study. But now let me explain this with the help of water, the phase diagram of water, where we will vary both the temperature and the pressure. So we'll be using plus 2. Let's see what are the possible components. For water case H2O, what is the component? There is only one component, which is the water, right? Now what are the possible phases? The possible phases are ice, water and steam, right? These are the three possible phases. Now we need to find, if we need to find out the degree of freedom at any place, we need to identify how many phases are there at that place. So to begin with, let's say we want to examine this location. Here the only phase available is ice, right? Since only phase available is ice, we will take P as 1. Component is already 1 fixed for all the phase diagram. Therefore degree of freedom over here, F, if we calculate, comes out to be 1 minus 1 plus 2, which is 2. Now when I say 2 is the degree of freedom at this location, what does this mean? This means that I can independently vary temperature and pressure here at this location and still remain in the ice phase itself. Let's say I increase temperature by this much and increase pressure by this much. I reach this new location, but still we are at the ice phase. Okay. A point to note that when you change the temperature and pressure, these are infinitesimally small changes. Here I have done just to exaggerate the change, but degree of freedom means that there will be at least one combination of change of temperature and pressure which will again give the same phase or phases. Okay, so this means temperature and pressure both can be changed independently, thereby we have 2 degree of freedom at this location. Similarly, if we take any steam location, we go change temperature, change pressure, 2 degree of freedom. Similarly, over here in the water region too. But now just imagine you are at the interface of ice and water over here. What is happening now? Now what is happening is you have coexisting ice and water at this location. Thereby the number of phases no longer is 1. For this location the number of phases turns out to be 2. Therefore degree of freedom is 1 minus 2 plus 2, which gives me 1 degree of freedom. What does this mean? This means that temperature and pressure cannot be varied independent of each other to remain at the two-phase region. The two-phase region is basically this line. So if we change the temperature from here till here, then there is only one possibility of pressure, that is the pressure should come down till here for the system to remain in the two-phase region. Therefore there is only one independent variable, right? If we change the pressure from here till here, then the temperature needs to be reduced till here. There is only one possible combination of temperature and pressure. You see that? So the degree of freedom basically says that there is only one possibility, one independent variable to remain in the dual phase line. Similarly over here, if I change the pressure from here till here, then the temperature must be changed from here till here. That is the only possibility to still remain in the dual phase line. Okay. In addition to the dual phase line, we have what is known as the triple point. Now let us check out at the triple point what is the degree of freedom. At the triple point, the phases that coexist are ice, water and steam. All the three phases coexist. Therefore the P, the number of phases over here, is 3. It's not 2, it's 3. All the three phases coexist. Therefore the number of degree of freedom for the triple point will be equal to number of components is 1, that is H2O, minus number of phase is 3 plus 2, that gives me 0 degrees of freedom. What does this mean? This means that I cannot independently vary either temperature or pressure. There is no degree of freedom at all. The other way to put this is that triple point is a singular point. It's an invariant point. It's an invariant point. This is only possible at this particular point. There is no alternative point. So if you recall back the eutectic reaction, the eutectoid reaction, the peritectic reaction, those were invariant points. They were possible only at a given temperature and composition. Here we are dealing with temperature and pressure. Over there we needed to deal with temperature and composition. Over there, let me jump back actually. Over here, let's see degree of freedom in this case. At this location, we have the phases are delta, gamma and epsilon. So we have all the three phases coexisting at this point. Okay. The components we have are 2 here. In water we had one component, which was H2O. Here we have zinc and copper. So we have 2 components. But since we are in the solid state regime, we are keeping the pressure constant. Therefore degree of freedom can be found out to be P, let me recheck, C minus P, C minus P plus 1, because pressure is constant. This gives C is 2 minus 3 plus 1 is equal to 0. So we see again here using the Gibbs rule that at this invariant point also we have degree of freedom 0, which it should have because it is a singular point like the triple point of water. Okay, so this kind of gives you a rough idea about what Gibbs phase rule is and how using the Gibbs phase rule we can engineer the different combinations of temperature and pressure. We can play around and we can decide what temperature and pressure, or what temperature and composition we need to take, or which are available for a process to have the given phases that we require. Fine. Now I will briefly talk about ternary phase diagram. Till now what we have done is we have been talking about binary phase diagram. Binary phase diagram had two components. Ternary phase diagram has three components. There are three component systems. Now since there are three components and another variable, the fourth variable will be temperature, right? So in order to represent it in a phase diagram, you need three dimensions. Therefore ternary phase diagram are quite difficult to make. Alternatively, there are methods to represent a ternary phase diagram in two dimension also, but you can imagine when you are trying to shrink three dimension into two dimension in such a way that all the information of three dimension is passed on to two dimension, then the two dimension representation is going to be quite haphazard, and it is a really challenging task to actually study a ternary phase diagram. I'll not go into the details about ternary phase diagram, but it is available, and all the three component systems are represented in 2D using ternary phase diagrams. Okay, with this I will stop today's lecture. Next lecture we will discuss about the much talked about iron carbon phase diagram. Why do we focus so much on iron carbon phase diagram? This is because iron and in turn steel is the fundamental backbone of all the construction and all the recent human developments that has been going around. The industrial revolution revolves around iron and steel, and that is one of the basic reason that iron carbon phase diagram is the fundamental that any student of material science and metallurgy ought to know. Next class we'll see iron carbon phase diagram. Till then, have a great day. Goodbye.